Good morning. We will see this morning how to solve the inverse kinematic problem for a robot manipulator using a numerical approach. So this slide is the presentation slide of the comparison between looking for an analytical solution in closed form or looking for a solution by applying a numerical method, which is typically an iterative one. So we are here, and we will introduce now two approaches, one based on Newton method and one on the gradient method. And then we will compare the two analytically and also on a numerical example. The basic aspect, the basic tool that we will use is the Jacobian matrix associated to the direct kinematic map. Or in a more general sense, if we want to find joint variables for a robot that are associated to a desired value of some task, then f of r of q will be the task kinematics, and we will use the analytic Jacobian of this task kinematics. This is why we have introduced this concept in a more general sense. So, when do we resort to a numerical approach? There are different cases, either when we are sure that a closed form solution to our problem does not exist, and we are sure every time the number of generalized coordinates is larger than the number of task variables. So when n is larger than m, in that case we know that the standard situation is that we have an infinite number of solutions, so we cannot write them in terms of a function of the data. Okay? Or when we are not sure if a solution exists, for instance, when the sufficient condition of Pieper are not satisfied, or even if they are satisfied, we are too lazy or we don't want to bother about looking for an analytic solution with the techniques that we have introduced last time. Okay, so we resort, so what we need to do is to compute the forward direct kinematic or task kinematic, how do we want to call it, f of r of q, and build this matrix with partial derivative in the way that we have illustrated on the blackboard, I think last lecture. Okay, so with this matrix, which is in general an m by n matrix, we can introduce the different numerical approach. First, we will start with the Newton method, and I will introduce it here first for the case where this Jacobian matrix is square. So how does the Newton method work? So remember that we have to solve some, this is in this case m, this is n, and we are considering m equal to n. We can rewrite this as Rd minus f of r of q equals 0. So this is a set of nonlinear equations to be solved. How does Newton method works? Well, it tries to linearize, in a sense, in approximate way, those equations around some initial guess and solve the linearized version of this equation. And then this will be the new guess. So the system of equation is linearized around the new set of equation, and so on and so on. Okay? So you have to use, in order to linearize this is linear. This function is nonlinear. It's a trigonometric function, typically. So we have to expand this in Taylor series and stop at the first step. So here I'm rewriting this in this form. So suppose that we are at the current estimate of our solution. Qk, pay attention, is a superscript, so this is the kth iteration. It's not the kth component. It's not the kth joint. It's the vector q evaluated at the kth iteration. Okay? So we expand this nonlinear function with a starting point qk. So we evaluate the function at qk, and then we take the partial derivative of the function with respect to the variable q, which is the Jacobian, and we evaluate the Jacobian at the current point of expansion, so in qk. Multiply by the first variation, q minus qk. If we add also the rest of this Taylor expansion, we know that this is something that is an order of magnitude at least square to the norm of the difference between the point where we are, generic point, and the initial point of the expansion. Okay? This is the standard case. So here we have equality with those terms which are complex and we don't want to care too much. But if we assume that we are close enough to where we want to be, so to the point that such that this equality is satisfied, so we are solving the problem, then it means that we will work only around qk, so these terms can be neglected because it's a second order term. Okay? So this time, if we remove this, we should write here approximately equal to. Okay? But in fact, Newton method just takes this as an equality, and now you see that removing that part, this is constant, and this is a linear function in Q. So that should be chosen so that it equals the desired value of R. Okay? Very simple. How do we solve this? We solve this by inverting the square Jacobian. Okay? So we solve for this, and we call this solution the next guess. So the next guess, if you rearrange things, will be the previous one plus the inverse of the Jacobian evaluated at the previous guess times this difference. Okay? Clear enough, I think. No? Now, look at this. This difference is what we call the task error, because it's the difference between where we would be with our current guess, so f of r of q of k, so the direct kinematics, and where we should. If this is 0, then we have solved the problem with qk, and in fact, if this is 0, we don't update qk, so qk plus 1 will be equal to qk. Okay. Otherwise, we will update it by taking the error, multiplying by this inverse matrix. It seems strange, but and then having a new guess. Okay? And then you repeat until the error goes to 0, hopefully, or goes below some final accuracy value that you have chosen in advance. This is the Newton method. Now, if you haven't never encountered this method before, you should know that it converges because it's based on this expansion, if the expansion makes sense. So if we are close enough right from the beginning to the solution. So with our initial guess, Q0, is already close enough to sum, and pay attention, sum Q star such that this is the solution. Why I write sum? Because we have already seen that there may be multiple solutions to the problem. Okay? So provided that I start close to one of this method will converge to that solution and not to another one. Okay? Of course, if I restart from a different point, close to another solution, I will converge to that solution. Numerical method can converge only to one solution at a time. So if you want to generate more solution, you have to restart from different initial guess. Okay? Second point. Here we need to invert this matrix. What if we are getting to an estimate such that this matrix is ill-conditioned, so it's nearly singular, or even completely singular? So we cannot invert this. So we have to put in some check. Before inverting a matrix, we should check that the matrix is invertible. This check should be coded in our algorithm. But the point is that not only if we are in a singularity of this matrix, but even if we are close to a singularity, so we can still invert this matrix, but the inversion will be 1 over the determinant, and the determinant will be very small, which means that even if this is small, we will amplify this update, and we will move very far away from the current QK to the new QK plus 1. So the system, the iteration becomes unstable because we are in a QK plus 1 will be far away, and then from QK plus 1 we will get another point in the configuration space as a possible solution, which is very far away again, and so typically you don't converge at that time. Okay? So there are problems in singularity, certainly, because we cannot invert the Jacobian, but also near singularity. And how near, it's a matter of putting limitation. Okay? Another problem is what, here we have written the Newton method for the square case. So when m is equal to n. What if we have a problem where we want to find, for instance, we have a planar robot with n equal 3, and we would like to find some configuration, some value of Q1, let's say Q1, Q2, and Q3. Pay attention, these are the theta of Denavit-Artenberg, such that the end effector is here. Okay? So this is position, desired position in the plane, so in R2, so m is equal to 2 and n is equal to 3. The Jacobian in this case will be a 2 by 3 matrix. Okay? So even if it's full rank, what is the maximum rank of a 2 by 3 matrix? 2. Okay? Even if it's full rank, we cannot write an inverse of a non-square matrix. Okay? So this is not too bad because we replace this by a so-called pseudo-inverse, which is a 3 by 2 matrix. Okay, first of all, the dimensions are twisted. And if, we will come back to that later, but the pseudo-inverse of this matrix, if rank is equal to 2, or if the rank is full in general, is this matrix, J transpose R of Q times J R of Q, J transpose R of Q to the minus 1. Okay, you see that you take this matrix, you make the product for its transpose, so it becomes a 2 by 2 matrix of full rank. You invert this matrix and you pre-multiply by the transpose, which is again a 3 by 2. So you have a 3 by 2 matrix that you replace to the standard inverse. Okay? Even in this case, however, if this is not full rank, or the two rows are almost linearly dependent, then you have problem even with this formula, because here you have an inversion. Okay? And more in general, you have the same problem. You don't solve everything with this, but at least out of singularity, you can replace the inverse with the pseudo-inverse when the problem is non-square. Okay? So very many problems in that, because, for instance, this is very critical. Because what does it mean, close enough? How can I say in advance if I'm taking a guess which is good or not? I could say, okay, take this guess. If I converge, it was good. If I don't, it's not good. But I would like to avoid such situation. Okay? On the other side, there is some positive aspect. When this method converges, it has quadratic convergence rate, okay, which is the fastest possible rate of convergence that you can have of any algorithm. Okay? So if you do the ratio of the error from one iteration to the other, this ratio falls down with the power of 2. Okay? So it's very fast, stated in a simple way. So what does this Newton method? Why there is an inverse? Maybe you know this method from elementary calculus as a method for solving a scalar equation, not a vector equation of a vector unknown, but a scalar equation of a scalar unknown. Okay? So for instance, if you want to find the root of f of x equals 0, a single equation, nonlinear, of a single scalar value x, suppose that this is f of x, and you want to look for this point which solves f of x equals 0. So Newton method set up this type of iteration. Okay, and here you have an animation of what happens, starting from, you start from this guess, you have this value, you go along the tangent, you find the 0 of the tangent, you have this point, tangent, this is the new estimate, go there, tangent to the function, and so on. Okay? And this converge if the function is not strange, is smooth enough, and you're starting close to a regular situation. If the function has a lot of bounces like this, you may go to another point, and you may not really converge if you're not close enough. Okay? So have you ever encountered this type of behavior? Okay? So what we have seen with the Jacobian inverse is the generalization to the multidimensional case of this method. In fact, this is 1 over the derivative. If the derivative is a matrix, so you have to do the inverse, not 1 over. Otherwise, it's exactly the same. Okay? I hope this helps you in reminding. Okay, so this is the presentation. We have seen the goods and the bads. Let's introduce now the other method and then compare them. The other method is the so-called gradient method or max descent. Now, the gradient of a function is the direction along which the function increases. Okay? If you have only a scalar function of a function of a scalar variable, like in the previous case, the gradient is just the direction if either x increasing or x decreasing where the tangent is positive. Okay? In a multidimensional setting is a direction in the n-dimensional space where you are a guarantee increase of the function, at least if you're moving very little from the current point. Okay? So why do we need a maximum ascent if we want to solve a set of nonlinear equations? Because remember, we have to solve this set of linear equations. Well, this is a nice trick. So we build a function on the problem of solving a set of nonlinear equations such that this function is always positive if we are not in the solution, and is 0 if we have a solution. So we would like to find the minimum of this function. If we find the minimum of this function, then we have solved the problem. And since we have to minimize a function, instead of using the gradient so the maximum ascent, we will use the negative of the gradient, which is the maximum descent. Okay? It's just a matter of changing sign. So what is the function that we want to minimize? And what is a nice function? Well, for instance, the square norm of the error. Okay? If you look at this function, the factor 1 over 2 is just for avoiding a factor 2 in the derivative. It's irrelevant. This function is certainly 0 if we are in a solution. And otherwise, if Rd is different from R of f of R of q, since it's a norm, it's always positive. So it's a good candidate. It's always positive and 0 in any of the many solutions. Okay? So we want to minimize this function. Remember that the square of the norm, you can rewrite it like this. So a row vector times a column vector. So it's the sum of the square of the component of the vector, and the vector is Rd minus f of q. Okay? So this is the function, and the gradient method for minimizing a function, pay attention, is same thing. An iteration, so you have a guess, q of k, and the new value is the previous value, but you make a step in the direction of the gradient, actually of the negative gradient, by a step alpha. And step alpha should be decided. Okay? So you remember this notation. The nabla means the gradient of this scalar function h, about there, and then you take the transpose so that it becomes a column, so that you can add to this column, which is the configuration vector at step k, this other column to get the new estimate qk plus 1. So let's do this computation for that. So this is the general method. This is the function that we need to minimize for solving our inverse kinematic problem. So let's compute this. So, and I will compute it by taking first this derivative. Let me so I have to take the derivative of this function, and q appears here and there, and in fact it's the same factor twice, so I take only once the derivative and then double it. And since I have a factor 1 over 2, this 2 disappears. Okay, so the derivative of this is a row, remember, so I'm taking first Rd minus f of Rq. And then I have to take the derivative of the term which is inside the square bracket. So I have to take the derivative of f with respect to q. And there's a minus sign here, so I have a minus here. And then I have derivative of f of r over q. Okay? And this is this expression. What is this? It's the Jacobian of the direct kinematics, so I can write it again. Minus Rd minus f of r of q times Jacobian. And then I take the transpose of everything. So I will have d of h of q. So it's the transpose of this, which is the transpose of this, which is nothing else than minus jr transpose of q times Rd. Sorry, there was a transpose here missing. Okay? Clear enough? How does this Jacobian transpose comes out? Just of the taking the derivative and doing things. So we have just computed this expression, and now we replace this expression into the general form of the gradient method for minimizing a function. So this minus sign cancels this minus sign, and this is the final iteration that you have to set up. It's very similar to the previous one. You see, you have the current estimate qk, you have an error at the current qk. If you don't have an error, you have a solution. So this goes to 0, so you don't update. Otherwise, this error will be now multiplied not by the inverse of the Jacobian, by the transpose of the Jacobian. Okay? And this will multiply by a scalar alpha, which is positive. And then this will give the update. So you can immediately comment on the comparison. This is more complex or less complex than the Newton method? It's about the same, no? Same thing, the only difference is there's a scalar factor here that we still need to choose, and we are using the transpose instead of the inverse. It's better or worse? It's better. For instance, even if this is singular, we don't care. No? We have no problem of explosion of terms. Even if the Jacobian is non-square, this makes sense. It's the transpose of the non-square Jacobian. It's just exchanging rows and columns. Okay, so it's insensitive apparently to singularities. Works in any case, square or non-square, and it's simpler because transposing is an operation at cost 0. If you have the Jacobian, it's just considering the index exchange of the rows and columns, while doing the inverse is something that costs in terms of computation, even if the inverse exists. Beautiful. 3 positive aspects. Now, the limitation. Okay, first of all, this step size, alpha, should be positive. Why? Because I have found a direction where I descend the gradient, the negative gradient. If I take alpha negative, I'm going to the other direction, so I'm going where things increase. So it's positive. But how large should be this? Now, this is a trade-off. If I take it very small, say 10 to the minus 6, then I'm guaranteed that I'm taking a step in a direction where the function decreases, because it's local. Locally, I found that if I go there, I decrease. If I make a very small step there, it's certainly that I will decrease. But I will not move my estimate, because if this is 10 to the minus 6, qk plus 1 will be very close to qk in any event. So I will make very small steps toward the solution. Very means I could take 100 iterations to go to the solution, which is too much. Okay? If I take a large step, then there is no guarantee that this will still be a direction of descent. So the direction is descent only locally. Imagine that, I always make this example. You have made an excursion in the mountains, and now it's late in the evening, it's dark, you don't see anything, no stars, no lights, but still you have to go down in the valley. So what you can do is just explore with your feet where is the direction of descent. And you make a step in that direction. And here I'm going down. Now, if you're in a valley like this, if you take a too much large step, you will even increase your height. So you're not guaranteed to decrease. Okay? And since this function may be very complex, we will see some shapes in simple cases. This cannot be too large. Otherwise, you're going locally, it would be a good direction, but if the step is too large, trying to speed up the method for convergence, then you cannot guarantee that you decrease the error, okay? Which is the function h that you're trying to minimize. And then even if you're close to the solution in particular, the solution may be some deep valley like this, and suppose that you're here, and so if you make a small step, you will decrease, but if you make a large step, or even like this, you will increase, and then you can zigzagging and never find the solution. Okay? So you have to really smooth down this alpha eventually. And this is what we said. So there are aspects which are problematic. Okay, but does this converge? We have still not said that it converges. Said, okay, small step, I may be slow, but I know that I'm going down. It converges all the time. What happens if the Jacobian becomes singular? We said that the method stands by itself, no explosion, but does it converge even in that case? So in order to study this, it's not strictly necessary, but it's very nice to use this equivalence in terms of a feedback scheme. After all, both the Newton method and the gradient method are taking an error and they're trying to move the solution so that this error decreases, which is the task of any control based on feedback. No? If there's an error, I'm trying to reduce the error, and so I command the system in such a way. So look at this equivalent continuous time representation. Remember that formulas that we have written are not in time. They are just increments of an algorithm. They are step of a sequence of points. There's no time, no motion involved. But suppose that you have this type of dynamic system. So Q is the configuration. Q dot is the velocity of the joints. So when you integrate the velocity, you have the position starting from an initial position Q of 0, time 0. Now, in any configuration, you're computing the direct kinematics. So this is the current value of R, or of the task. And you compare it with the desired value. So you generate an error. This is RD minus f of R of Q. So it's the error there. And then you multiply by the Jacobian transpose. Actually, there's an alpha missing here. In fact, I just said for the illustration alpha equal 1. Otherwise, you can put the alpha wherever you wish. It's a positive scalar. You can put it. And then you generate a velocity, which means you're moving. And then you integrate. You're getting into a new configuration. You compute again. So you have set up like a controller, where the controller is this Jacobian transpose. And in the feedback path, there's no unity feedback, but there's a function. Now, probably you don't realize this, or nobody explained it in this way, but you should think that if you have a feedback system which is asymptotically stable, so it converges to something, it will automatically invert from the input-output point of view what is in the feedback path. This is why we refer to unitary feedback, because if the feedback is unitary and we are inverting this, then the output will be equal to the desired value, which is put in input to our controller. Okay? So if this converge, or the system is asymptotically stable, and where in an equilibrium, and the equilibrium is E equals 0, because if E is equals 0, J transpose of E is 0, then the velocity is 0, so we are not moving, we are not integrating, we remain in the same configuration, which generates the same value, which is 0. So this is the equilibrium. If this equilibrium is asymptotically stable, then automatically we will find there the inverse of this applied to the desired value. So exactly we are solving the inverse kinematic problem. Okay? This is the way on interpreting this feedback path. Now, how do we study the fact that E equals 0, is a closed loop equilibrium, but that this is asymptotically stable, which means no matter where you start from, and no matter which is the value of RD, this will converge to a solution, so to E equals 0. If the system was linear, we would look at the transfer function, the poles of the closed loop. If these are in the right-hand side complex plane, then this is asymptotically stable. Okay, or if we give a state space expression, we look at the eigenvalue of the closed loop matrix. If these are, again, complex with negative real part, then we have asymptotic stability. But here we have a nonlinear system, because the variable is q, and these are nonlinear function of q, both f of r and j of. So how do we study stability? In that case, we resort to the so-called Lyapunov methods. Have you ever heard about Lyapunov methods? Well, even if you haven't heard about that, Lyapunov is very simple. So you take a function, and not by chance, this function is just the square norm of the error, exactly what we defined before. And this is a function which is always positive and 0 only when we are in the solution. Okay? Now, if we are able to prove that this function, no matter where it starts, so where we start with q, so this function will be different from 0, positive. If we are able to prove that this function can only decrease, then, and since it's lower bounded by 0 at the solution, it only decreases, so it will converge to E equals 0, which is the solution. Okay, very simple. So we're just looking at one scalar function, even if the system has 250 joint variables, we can decide upon convergence. Okay, so it's a very powerful result. So look, how do we see if this decreases? We should look at its time derivative. So v dot, if decreases or if it increases. So v dot is computed as follows. Again, the error is an implicit function of time because it's a function of q, and q is a function of time. So I have to take the derivative of this function with respect to e, and then the derivative of e with respect to time. This is a quadratic, so it gives e transpose, and then the derivative of e with respect to time. Okay, it's more or less what we did before there. Now, e dot, which is the derivative of this expression, this is constant because it's the desired value of our task. And this is, again, a function of time through the fact that q is a function of time. So we have to take the partial derivative of f with respect to q and of q with respect to time. The partial derivative of f is the Jacobian. There's a minus sign here, so we have minus A transpose Jacobian. And then the derivative of q with respect to time is q dot. Okay? And now where we look at q dot? We look at q dot in the block diagram. Q dot is equal to J transpose E. So you see that here we replace J transpose E. And this is a vector, and this is the same vector transposed. So this is the square norm of a vector with a minus sign. So this is always less or equal than 0. Okay? And in particular is 0 if the error is 0. Unfortunately, is 0 also when the error is not 0, but belongs to the null space of this Jacobian transpose matrix. You see that? There may be cases where the error is not 0, but when I multiply this non-zero vector by a matrix, J transpose, I may get a 0 vector. When does this happen? When the vector E belongs to the null space of the Jacobian transpose. And when does the null space contains non-zero vectors? Only if the matrix loses rank. So we see that singularity here are a problem in the sense that the method does not converge if we encounter a singularity. It just stops. Because what happens? Suppose that E is different from 0, but JR transpose of E is 0. This means that V dot is equal to 0, so it stops there. And in fact, J transpose E generates Q dot equal to 0, even if the error is different from 0. So we get stuck in some configuration. which is not a solution. It's not too bad, because we can check this in our code. If the iteration does not update things, and the error is still different from 0, and we know that the error is still different, we recognize this, so we may restart with a new guess. We may perturb the solution to get out of the singularity and of the null space. Okay? While in the previous case, if we are getting in a singularity, we have an overflow of values, and we lose control on our program. So there's a big difference in terms of implementation. Okay? So, summarizing the properties of the gradient method, it's computationally simpler because it requires only the Jacobian transpose and not the inverse or the pseudo-inverse in case of non-square. Can be used directly in the same way if the robot is redundant for the task, so the Jacobian associated to the task kinematic is non-square. May not converge because it may get stuck, like we have just seen, exactly when our Q enter into the null space of J transpose, and this null space is not just a 0 vector, but it never diverge, like instead the gradient method, the Newton method. Now, the previous continuous time analysis, if you go back to this block diagram, and you see what is doing Q dot. So Q dot is J transpose of E. Now, suppose that you want to implement a discrete time version of this, which means that you replace Q dot becomes Q k plus 1 minus Qk divided delta t, an approximation of velocity. No? The velocity is just a variation of position divided by some sampling time. Okay, so let's do this and then reorganize things, and you find this kind of discrete time version of this feedback scheme which was defined in the continuous time. And this is exactly a step of the gradient method if you replace delta t by alpha. Okay? So you see that there's a strong analogy of the two, and this tells you also that alpha should be small. In fact, if you're taking a big alpha, is like taking a big delta t here and approximating the local velocity at configuration k with some increment, but which is taking over a large time, so you lose information, local information, which is typically of velocity. Okay, so this tells you that alpha should be small enough, not too small, but small enough, at least if you give this interpretation. Well, since we have worked in this way, in a Lyapunov, with a Lyapunov analysis, the same analysis tells us that we can replace the scalar gain by, the scalar gain will be alpha J transpose E, or even J transpose alpha E, because the scalar alpha can be put anywhere. Now you can replace this scalar by a matrix K, and the matrix should be put in front of the error, which means that, suppose that K is a diagonal matrix. So you are trying to emphasize an error in one direction with respect to another direction if you take a diagonal K with non-equal gains on the diagonal. No? You're saying, I have a small error on joint 1 and the same small error on joint 2, but I care more about the error on joint 2, so I amplify the error on joint 2 by taking K2 on the diagonal bigger. Okay, so you can be more flexible. The analysis would be the same, but I hope you can follow me now, even if I'm getting more abstract. You would need to take a Lyapunov function candidate which is like this. Okay? If you're moving from alpha to a positive definite K matrix. Okay? And this would be the update. It works in the same way, but you have more flexibility in choosing K to accelerate convergence of some component with respect to other component. And in addition, remember that if you replace K by K plus K skew, so you add the skew symmetric matrix to matrix K. You remember that we said that in quadratic form what happens to the skew symmetric part? 0. So this means that this is also equal to K plus K skew. So the same analysis that you do here, you do it here, just because this disappears when you put this. Okay? So this trick can be used when you're reaching a stationary point. Suppose that during the iteration, the error, you get close to a singularity of the Jacobian transpose, and the error enters into that null space. So the system stops. You have a stationary situation, even if the error is still different from 0. Okay? Now, how do you let this method restart in an automatic way? Just by adding to your K a skew symmetric matrix, which will rotate the error so that even if you're in a singularity, the error is out of the null space of this matrix. And the system restarts automatically. If it restarts, it will move from the current Q to a new Q, and it's very likely that this new Q will not be in a singularity. Okay? So it's a very handy way to going through the singularity and restarting automatically. And all this can be included in a software code to make this method more robust and more efficient. Okay? So let's do a case study first, analytical case study. So I will write down the equation that you need to implement with the Newton method or with the gradient method for a specific case. For instance, suppose that we have, no wonder, our good old friends, the planar to R robot with equal link length. So very simple case. And equal to 1, just because I don't want to carry things. And suppose that the desired end effector position is 1, 1. Now, what is the solution to this problem? What is the inverse kinematic solution? So we are some set of coordinates. We have a link 1 and a link 1. And now we would like to be here. This is our desired 1, 1. What are the inverse kinematic solutions for this? I've chosen this exactly because I can see it very simple. Remember, this is 1 and this is 1. Come on.
Just put the first link on the x-axis of the y-axis and the other one.
Okay. So this is a solution Q equal 0, 0, pi over 2. Okay? It's the only solution. Okay, the other is this one. Let's call it Q prime, and Q double prime is pi over 2 and minus pi over 2. Why minus? Because this is positive because it's counterclockwise, and this is negative because it's clockwise. Okay? So we have the solution for this, very simple. Okay? But still, we may not wish to look at this graphical case, so we write down the, remember, you have to write down the direct kinematics, which is this one. L1 is equal to 1, L2 is equal to 1, so this is the direct kinematics for the x and the y coordinates. Then you have to build up the error. Desired R minus the direct kinematics, so 1, 1 minus this expression. Okay? And then you have to build the Jacobian. Sorry. The Jacobian is the partial derivative of the vector function with respect to Q1 and Q2. So, first component is C1 plus C1, 2. So I take the derivative with respect to Q1 is minus S1 minus S1, 2. Then I take the derivative with respect to Q2 is only in the second term, which is cosine of Q1 plus Q2. So it's minus sine of Q1 plus Q2. And same for the second component. With respect to Q1 is cosine of Q1. With respect of Q1 is cosine of Q1 plus Q2. With respect to Q2 is only the second term that matters, is cosine of Q1 plus Q2. Okay? And then, if we want to write the Newton versus the gradient iteration, here is the error. 1 minus the first component, cosine plus cosine. Second component is again 1 minus sine of sine. All evaluated at the current configuration QK. And then here you have the two options. So the new update, so you start with Q0, then you will generate Q1, and then Q2, and so on. So it's the previous version, plus here on top, you have the expression of the, you don't see anything. Oh, anyway. Here, this is the inverse of the Jacobian, and this is just the transpose of the Jacobian with the factor alpha in front. Okay? So you can immediately have it's different. This is just transposing rows and columns here. This is the minors. So in a 2 by 2 matrix, you know that the inverse is 1 over the determinant, which is sine of Q2, the determinant of this matrix. And then you exchange this and you change sign to this. This is the inverse of a 2 by 2 matrix. So both are evaluated at the current QK, but if you're getting close to a situation where Q2 is 0, you see that this will generate a very large value. Okay? But otherwise, I mean, they look similar. This is the error. Is the same, and then either you have this or you have this, so the Newton or the gradient method. In the gradient method, you still need to choose alpha. So you typically may start with a small alpha and keep it constant, or try to update. There are optimization technique which makes a line search, and in that direction, choose the alpha that is most convenient for descent. Not too small, but not too large. May approximate the function with a quadratic function in that direction and take the minimum of that of the function in that specific direction, which is an easy task. Okay. Now, let's look at this in a graphical way. Let me see if I can improve the quality of the color. No? Again. No. Okay. So, no. Okay. Okay, better. Okay, that's it. Okay. Slightly better. So this is the situation. It's very convenient here because I can use MATLAB to represent valleys and hills, or just iso-level curves, because we have only two variables. Okay, so we have Q1 here and Q2 here, or Q1, Q2, and this is the function of the error function. For that specific values, pay attention, for 1, 1, otherwise it would be different. So you see that if you start here, you should go down and find the valley here. Or here maybe it's more clear. If you start from here, you would like to find either this or that solution, which are exactly this solution and this solution. Okay? Without knowing the whole picture, but just deciding locally where is the direction of maximum descent and making a step in that direction. Okay? There was some more comments on that, but I mean, we don't care now. So, suppose that this is, again, the same situation, but it helps me, the two graphs helps me to tell you all the possible cases that can happen. So first of all, so we know that these are the two solutions. Okay? So depending on where we start, we may, for instance, start from there, just by chance. We throw some configuration, and then we follow the maximum descent direction, which means that we move always orthogonally to the iso-level curves in the direction of descent. This is why we're going up, because this is approximately normal, and then we find this solution. And you see that at the end, the iso-level curve tends to flatten down, so if we take a step too small, we may need more iteration to get there. These are some numbers of iteration we don't know. It's just a graph that I throw. Of course, and this is the solution 0 pi over 2. Indeed, if I start from a different point, for instance, from here, I will get there. Now, you can imagine that there is some separation area. That if I start from one area, I will go to one solution. If I start from another area, I will go to the... Do I care about that? Not really. But more or less, I can imagine there's a boundary here that separates the two regions where we have only one solution. And in fact, the boundary is where I'm keeping the right arm solution all the time, and then when I stretch, I go to the left arm solution. Now, this is the right and left arm solution. Okay? Now, when things can go wrong. So look at these points. This point and this point. If you remember the figure, there was a maximum somewhere. Okay, so this is a maximum. It's the highest point of the hill. Okay? So if I'm in a maximum, locally, pay attention, locally, so if the step is small enough, I don't see any direction where I can go down. So this is a stationary point. So if I start exactly from the maximum configuration, the algorithm will not move. Okay? The gradient method will not move. This means that the error, which is present, because of course, if I'm here, I have this error or this error, depending on, better say, the error is in the Cartesian space, but I have some error related to the fact that I'm not in one of the two known solutions. There are no other solution. Okay, so I will be stuck here. And I will be stuck even if I start from here. And this is a saddle point. Because if you, I should draw more lines, but these are two minimum. Here you have an increase, and here you have a saddle point. So if you go there, you increase. If you go there, you decrease. So you have a situation where you have a saddle. So locally, no direction where you can descend or go up. Okay? So if you start from there, you're stuck. There are only 2 points. You have to be very unlucky to start from there. But in principle, the system is very simple. Even in this system, simple system, you have this situation. Or you may end up, pay attention, to the saddle point, you may end up even if you start from somewhere here or here, because you start moving and then you end up here, and now you don't have any direction of descent. Of course, here you don't start at all, because you're on the maximum and you stay there. Okay, so all this, this local maximum and saddle points are situations where the algorithm stops. But of course it can restart because you realize that the new iteration provides you the same value as before, and the error is not zero, so you are in a situation where one of these situations, so you just perturb things. For instance, you give a random perturbation, you move this gas here, and then you will end up there. Or if randomly you move it here, you will go there. Or from here, if you give a push to your estimate, you will go out of the maximum and then converge here or converge here, depending on where you move things. Okay? So things can be really improved in this way. Now, I would like to draw exactly for this case. Now, what does it mean that this configuration, which I can also approximately read from here, it's the one with maximum error. So this means that I'm the farthest away from the desired Cartesian point. So which configuration is in that case? Since this function is the error function, it's measuring in the Cartesian space the distance from where I should be, and since that is the local maximum, actually it's the global maximum, so it corresponds to which configuration of the arm? Can you see it? Skew symmetric to those, so like this. Like this. It's a guess. It's a good guess, but not really. There are even worse situations. Look, take this diagonal, and now straight the arm in this direction. Aren't you the farthest possible from the desired point? Remember that the workspace is a circle of radius 2. So you are on the boundary of the circle, and the farthest away from here, any other boundary point will be closer to this point. Okay, so this is the local maximum. Let's read it. What is the value of Q1 here? Huh? If we look here, it's minus 3 over, this is minus 3 pi over 4, I guess. Okay? This is Q1, and Q2 is 0, in fact. 0, pa. Okay? Why it's minus 3 over and not plus whatever? Well, because we are defining things between minus pi and plus pi. So this would be larger than pi, would be reflected into this one. Okay. Now remember, this is very important. Remember that the point that is here, Q1, Q2, is very close to a point that is here. Because this is almost minus pi plus epsilon, which is pi plus epsilon. Okay, or minus epsilon. So in fact, here I'm showing things in R2. But we should take this configuration space of Q1, Q2, fold it, and have a tunnel. But the same holds true also for the other variable. So we have this cylinder, empty cylinder. We should fold it. And then we have the surface of a torus, which is the configuration space. There I can see immediately if 2 points are close or far away. But it's no longer an R2 plane, okay? So it requires a metric on a curved surface. It becomes much more complex if you want to look at the global picture. We are satisfied with this representation, but just remembering that if we are close here, we may get to, for instance, if you're starting from this point, you may get to a solution going there and re-entering from here, okay? Just because those points are, in fact, very close. Okay, now I leave it to you to find what is the saddle point. What configuration corresponds to this saddle point? This means that there's a solution. By the way, you see that this is a singular situation. The arm is straight. In fact, only in a singular situation I could have a non-zero error, and the error is here. Let me draw it with a different color. The error is this vector. This is E RD minus F of Q. This error is in the null space of the Jacobian transpose, which is different from 0 because the Jacobian is singular. Okay? And the same thing happens here. There will be another configuration where we have a singular situation. And a non-zero error, but still J transpose times this error is 0, so we don't move from there. Okay, so think about this. Okay, now, what are the issues before implementing this? So first of all, we need to choose an initial guess. We have seen that this may be critical. In general, it's not. In any case, when we take a guess, at the end, the system will the method will converge, Newton or gradient. If we are close enough, we'll converge for the Newton method. It will, in general, converge slower but safely with the gradient method, but we will find only one inverse solution. So either this one or this one in this particular case. This generalized to no matter how many joints you want to consider. So if you want to obtain another solution, if you don't like the solution that you have found, you just have to, the only thing that you can do is restart from a different initial guess. Okay. And if you have a redundant arm like the KUKA lightweight downstairs, and you're considering only the inversion with respect to the standard classical task of positioning and orienting the end effector, so you have 6 variables in the task space and 7 joints, so you have an infinity of solution in general. So this method will converge to one solution of this many. Okay, and if you don't like it, you have to restart and restart, and for every new restart you may find a different solution because there are infinite solutions. Okay, infinite means not that any configuration is a solution. Okay, it's just a one-dimensional manifold in a 7-dimensional space. So still you have to look for it. Okay. Now what about the step size just for the gradient method? So these are rule of thumbs. If we take a constant step size, so we don't add any choice during the algorithm iteration, maybe this is good for the first iteration because it moves enough, but then it's too large for the final one. If it's too small, it's bad for the initial iteration, it's good for the final one. Because initially we go very slow, but when we're getting closer, we need smaller alpha, not to miss the final solution. I think that this is now clear. So the best way would be an adaptive rule, which does a one-dimensional line search, as I said, and there are different techniques. If you will take some course in optimization, you will find, for instance, the Armijo rule or the bisection rule, which means take an alpha, look where you would go, evaluate how much you have descended with your function, then bisect the alpha, so alpha divided by 2, do the same and compare. If you're getting higher, then keep alpha. If you're getting lower, then alpha divided by 2 is better, so you divide it even, and so on and so on. Okay? So very, very simple rule that can be implemented at every step Okay, and then you restart with the same adaptation at every step. Oh! Okay, good. When do you stop? So when you find a solution, what does it mean numerically finding a solution? You will never get 0, for sure. So you have to make some stopping criterion. One typical stopping criterion is Cartesian error, or task error. You should have RD, you have f of qk. If this is less than 10 to the minus 6, it's okay. You stop. Okay? Now pay attention. This is a norm of a vector. In general, this vector is, has different units. The components have different units, because if you have linear quantities and angular quantities, you may have, let's say, meters or centimeters and radians. Now, these are apples and oranges. You cannot say, I'm away 1 centimeter and, let's say, 2 degrees. It's better or worse than being away 1 degree and 2 centimeters? It's a nonsense question. Okay, this is why when you have this, you may decide to have different norms on the linear quantities and on the angular quantities. Okay, this makes more sense. And then another check that you can make is how much the algorithm increments. Because you have to test, it's two different spaces. This is the Cartesian space or the task space, this is the joint space, so the metric are different. You may be very close in the Cartesian space, but still have enough motion in the joint space so that it makes sense to make increment. So you should check also if you have not enough increment, means you're stuck, and then you look at the Cartesian error. If the error is below that stopping criteria, you have found the solution. Otherwise, you are in a singular case and you have found you are in a configuration in the null space of the Jacobian transpose. Okay. Last point, especially for the Newton method, is understanding how close you are to a singularity. Because if you're really running into a singularity, things explode. So you want to stop things before they becomes dramatic. And if you have a square Jacobian, you may look at the determinant. But even in that case, the determinant is an on-off measure. So if it's 0, the matrix is singular. But a small determinant compared to another matrix with a small determinant, maybe one is more difficult to invert than the other. So the determinant is not a good, very good measure of the distance from a singularity. And the better measurement is something that requires some linear algebra concept, like the singular value decomposition of a matrix, which is something that you can find also in MATLAB. But essentially, you take the smallest singular value, which should be positive, and if this is closer to 0 or below a certain threshold, then there's a warning. We are close to a singularity. Do something. Not continue blindly with your iteration, because if you're going with Newton, you may have divergence. If you're going with the gradient method, you may get stuck eventually. So let's make a numerical test, and then make a small break probably. Before doing this, just something that, remember that something that I realize is not written clearly enough probably in this. Remember that the gradient method, if it encounters a singularity of the Jacobian transpose, then it is not said that the system stops. It may stop. There's an additional condition. You should be in a singularity, and the error should be in the null space of this matrix. I will show you this with an example. So suppose that you are in this configuration, like before, and you should be there. Then the Jacobian is singular here, because it's straight. This is a singular configuration. And the null space is in a specific direction, this one, which is in the null space of J. So let's write here, E is in the null space of J transpose. This is the standard. Then the system stops. The algorithm stops. Now, suppose that you are in this configuration. Is this a singular configuration? Yes, because it's folded. The determinant is 0. But the error is smaller, but it's in the same direction as before. And if you think of this error like somebody pushing you toward the solution, so like having a spring of stiffness K, in this situation, first situation, you're trying to push something which is stuck in this. So you're working against the rigidity of the links itself. In this situation, I'm pushing it in a direction where the robot will move. So in fact, you are a singular, but the error is not in the null space of the Jacobian transpose, so you will cross the singularity without problem. So the next configuration will probably be this one, and then whatever, you will find eventually this solution. Okay? So remember, for the gradient method, being singular is a necessary condition for the method to stop, but not sufficient. You may be lucky, the error lies not in this subspace. We will see how to compute these subspaces for Jacobian when we deal with differential kinematics, where the Jacobian plays, again, a dominant role. Okay, so let's move to this test. And I've taken one of the robots for which we have computed a closed form solution to the inverse kinematics. You remember that. And now we would like to solve the problem with one of these methods. So I'm choosing as desired position the 1, 1, 1, x, y, z. The only parameter that, if you look back at the slides, previous slide where we found the analytic solution, the only parameter here is this distance d1 from the base to the shoulder. Okay, so I'm taking here 0.5. And then if we restrict ourselves to Q3 non-negative, you remember that, no? There are 4 solutions, but then we have found only 2 solutions when we consider Q3 only to be positive, which is the extension of the last link. Then the 2 solutions for this case, if I apply the closed form formulas, are these values in radians, and these which are computed from the previous one just by exchanging, adding, or subtracting pi. Okay? So these are the 2 solutions. So we know them in advance, so that we can make sure that our numerical algorithm converges to the right solution or whatever. So as I said, we have to define some thresholds. So here in this simulation or numerical computation, I would say, I've chosen 10 to the minus 5 for the maximum Cartesian error. 10 to the minus 6 for the minimum increment in the joint space from one iteration to the other. Then I set up also an upper limit to the number of iterations that I want to perform. This is a good rule because everything may work, then if you don't put this, you never end up with iteration, although he's cycling maybe among solutions. And then, just to make things simple here, I've taken the absolute value of the determinant as an indicator of a distance from the singularity, although I warn you that this is not the best thing to do. And if we are below 10 to the minus 4, then we believe that we are close enough to a singularity, and we should take some precaution at that point. Okay, so these are the data that I'm using for the implementation of the algorithm. Now I'll show you some results of performance with the gradient method and using different value of alpha, actually constant value of alpha, just to, so no adaptive version, or the Newton method where I don't have to choose anything else. And these numerical results are obtained with different, there's a first test having this as initial guess or other test with other initial guess. This one in particular is a singular start. So it's where the robot is in one of the singular configuration that we have found, in particular because cosine of 2 is equal to 0. And this is a double singularity. You remember that analysis because Q3 is 0, so I'm starting with the third joint completely retracted. And P2 is equal to 0, which means that the second link is on top of the vertical of the first joint. So here the rank of the Jacobian is equal to 1. Here the rank of the Jacobian is equal to 2. So in both cases it's not equal to 3. So the determinant is equal to 0. But there are two severity of singularity as we discussed already. Okay, so these are critical start. This is a generic start. And there's a MATLAB code that, if you wish, you can have. So this is the first test. It requires some, I mean, if you look at this, oh, it's horrible, but it's very simple. First is a gradient method, the first three plots. Here are the iteration, 0, 1, 2, up to 15, because I don't go beyond 15. And I see that if I'm taking alpha equals 0.5, why that? Just by chance. I see that it reduces, but then it goes close to 0, but here is very slow. It's almost flat. So this is the error. It should go to 0. Now, if I take a bigger alpha, so here I stop because I didn't converge yet to that accuracy that I've taken, but I reached the maximum number of iterations. Here I see that I go down after 2 iterations very fast, faster than that, because I'm taking a larger step. But here, all of a sudden, the error increases, means that I'm missing something. So I'm not converging because alpha is too large. The gradient method converges only if alpha is sufficiently small. Okay? So alpha equal 1 is no good. Alpha 0.5 is too slow. Then I tried alpha 0.7, something in between. And in fact, I converge. Now I stop in 11 iteration because I'm below the threshold for accuracy. Okay? Now, if I look at the Newton method in this case, I see that I'm going down. And by the way, to a value here is below 10 to the minus 5, no? It's 0.57 of that. Now in 5 iterations only, I go to 10 to the minus 8. You see, it's much faster, and it finds also a solution which is closer, even closer than the accuracy that I required. Okay? So, good for the Newton method here. And here you see on the 3 component x, y, and z, the error in the Newton method, how it changes. So the single component may increase, pay attention, but it's the norm that converge globally. So here you see decrease of the norm of the error at every step, while at some step a component of the error may increase. This is normal, not to be. And these are the evolution with the not converging method of the gradient, with the best gradient that I found with 0.7, and with the Newton. And now here I'm showing not the Cartesian error, but the evolution of the joint variable. Okay? And you see that when I'm not converging with the gradient, so this variable tends to stabilize. But look at the other. Look at the second variable. It's just cycling, okay, and increasing. This is why the error is increasing. With 0.7, I converge here, and With the Newton, I converge in 5 iterations, and I'm converging to the first of the 2 solutions shown in both cases. Okay? And you can see here, you can read it there, and I know that this was the value as analytically computed. Okay? Clear enough? So here I would conclude Newton is much better. Now look at this second test. Again, we are starting from a single singularity condition. And since the Jacobian, the 3×3 Jacobian is singular there, if I make a check of singularity before initiating the Newton method, I would say, don't go anywhere, you're singular, you cannot apply Newton method. Okay? So it doesn't move at all. Just, it's a flag, I cannot use Newton. If I don't make this check, and I try to hopefully use numerical approximation, whatever it is, look what happens to the norm of the Cartesian error. No? It's just jump up and down. It's important, I guess. So we have divergence here. And if you look at the joint variables, it's even more clear, because here you just see jumping up and down in the Cartesian space. Even if you think about in the Cartesian space, you cannot have an error for all revolute joints. You cannot go much far away. No? You stay always in the primary workspace. Okay? So the Cartesian error cannot increase more than a certain value. But in the joint space, you can increase the error because the joints start to fold and fold and fold, and you're considering this as a real axis. So you're not saying that after 2 pi you are in the same configuration. You're increasing pi and pi and pi, and so this is the way in which it's looked. And in fact, if you look at the joint evolution, here the first joint variable has jumped to 10 to the 16. Okay? Because I inverted a matrix which was practically singular up to numerical rounding, and immediately I got a kick in the joint space. Okay? So you should not use Newton in this case. With gradient, same value as before, it works. It works. Although starts toward the solution, but slowly stops. So here the joint variables are still, you see that do not change, and the error has not gone to 0. So I'm in a singular situation. I'm still in the singular situation, in a better situation because the error has reduced, but I didn't converge. So at this stage, I should restart the gradient method to go out of this null space situation. And finally, this is the third test. And this is a double singular start. So for the Newton method, again, I cannot use it. And if I start, it will really explode. And in particular, it will explode even worse than before. So MATLAB code will end the run with a not a number. So it goes beyond the accuracy, double precision accuracy of IEEE, which is 32 bits of values. So we can only use the gradient method, only the gradient method. And you see that in a first, at the beginning, it starts toward the solution. Then at this point, it goes out of the singularity. I can read it in the joint space because I know that the singularity is characterized by some particular value of Q2 and Q3. So when, in particular, Q2 goes out of pi over 2, then I'm going out of the singularity. So at this stage, I'm going out. In the first iteration, I'm already moving out Q1. And then slowly, once out of singularity, slowly I converge to the solution. Here I left the upper limit. I removed the upper limit. In fact, I'm converging to the accuracy that I required in 19 iterations, more than 15, which was my upper bound, but it converged, so it works, okay? And you can see that these methods, here I started in singular situation because I wanted to show some strange effect. But in general, you start, like in the first test, from some configuration, you don't know how close you are, okay? So you may need some combining method. And in fact, if you think a little bit about pros and cons of the two methods, the most efficient iterative method would be the following one. You start with the gradient method. You start with the gradient method because the gradient method will, unless you're very unlucky and then you need to change start, will slowly move toward the solution. So you're approaching the solution. But then you become too slow, for instance, 9th iteration in the previous case, and then at some point you switch to the Newton method, hopefully not encountering singularities, because if you switch to the Newton method, you know that eventually you're close enough, because you have already reduced the error with the gradient method for some iteration, and at that point it will converge quadratically, so very fast. So the best implementation would be an hybrid method like this one. What about the presence of joint range limits? In all this consideration, we never thought about joint ranges. The fact that, say, Q1 is only between minus 120 degrees and plus 120 degrees. So the fact that the intermediate iteration are non-feasible is irrelevant. It's only the final solution that should be inside the joint ranges. Okay, it's like with the analytic method. In the analytic method, you don't care about joint ranges. You find all the solution in closed form, and then you check if every solution is inside or not. If it's inside, it's feasible. If it's outside, it's removed. Okay? And here is the same. You do the iteration. If you converge, you find the final value. You check if this is feasible. If it's not feasible, you restart the system from a different configuration. Okay? This last comment requires more, a little bit of thought. So I could think of solving the inverse kinematic problem, not offline like I'm doing here. No? Suppose that I need to start with my KUKA lightweight arm with a certain position of the end effector. How do I bring the robot in that position? I have to solve the inverse kinematic, and then I solve the inverse kinematic offline. I find the configuration that puts the end effector in that position, and I bring joint by joint the robot to that. And then I start the task. So I can do this offline. So I can take more time, less time, I don't care. I may even run into problem, but after some attempt, I find a good solution. Okay? Now, there are many cases where this inverse kinematic problem needs to be solved online. So you are already in a desired pose for the end effector in a certain configuration, and now some sensor tells you that you should move from here to here. So you have to solve this as fast as possible, starting with which initial guess? With the current configuration of the robot arm. And while doing the iteration, you are starting moving the arm itself. So each iteration is a new configuration of the real arm. And then, lo and behold, you should be very careful in handling singularities and joint limits and so on, because otherwise the robot would get crazy. Okay? So it's no longer a problem on the computer in a numerical algorithm, which you don't care too much. It's the real robot that is moving. Okay? So suppose that you have a sequence of inverse kinematic problems, one after the other, let's say every 40 milliseconds. You need to be in a new pose for the end effector. So you need to be very fast, do as little iteration as possible, because you cannot spend time in doing this, and the robot should go to the next point, and then there's another point, and so on. Okay? So if you're out of singularities, the good guess for each of these new problems is to take the previous configuration as guess for the next solution, especially if these new poses are close together, close to the previous one. So in fact, you may need only 1 or 2 iterations of the Newton method in that case, because you're very close, just moving, moving, moving. But you should include the check of singularities, okay? And then if you have a singularity, then switch to the gradient and try to, hopefully the gradient will converge in, let's say, maybe 5, 6 iterations, but still within the deadline of 40 milliseconds before processing the next point, okay? So this is what I commented before. And this is just a reminder. We will see that this Jacobian type method, using the Jacobian, inverting the Jacobian, pseudo-inverting Jacobian, we will encounter them again when we're talking about control. And in fact, moving the inverse kinematic in an online version is almost control. It's almost feedback control, because I see an error, I'm in a good position. The desired pose changes, I see an error, I want to compensate for that. So I'm solving the new, for the new inverse kinematic problem. The main difference, so you will find many similarities. The only problem is that here, I'm not specifying a velocity, in fact, unless I'm considering things in a continuous time, like in the feedback scheme. I'm just solving for configuration. While when we will consider at the end kinematic control, we will deal with velocities. Okay, we will command velocity and motion in order to bring the error directly at the differential level. And again, at that differential level, we will find that the Jacobian plays the dominant role. Okay? So let's stop, and in 15 minutes we will resume.